Thank you very much, Hans. Thank you very much for organizing this meeting. It's extremely nice to be back for me. I didn't come back since the last meeting about 20 years ago. So same face, I still have a little bit less hairs, but otherwise I'm the same, I'm sure. And the theme is the same, so wavelets, but from a slightly different point of view. I'd like to tell a little bit about learning, high-dimensional learning, from images to physics. So it's a work that was done with many people at École Polytechnique and École Normale Supérieure, Joanne Brunat, Matthew Hearn, Edouard Royalon, Nicolas Poelvert, Laurent Siffre, Irène Wolfsberger. So I'd like to comment a little bit about wavelets to begin with. A lot of the applications of wavelets have relied on the idea of sparse representation. Sparse representation, obviously, for compression of signals, for noise removal, for inverse problems. In mathematics, about the same kind of property have been used to specify functional spaces through weighted LP norm, decomposition of singular operators through the Shor lemma, again using sparsity. In quantum physics, also, a lot of these ideas have been used, in particular the well-known coherent states, which are near this idea of near eigenvalues or sparsity of the operators. And what I'd like to show here is that the use of wavelet for high-dimensional learning are based on a somewhat different idea. Sparsity won't be here the core of the problem, but you'll see it will be related to the need of building invariants, nonlinear invariants, over groups, and sometimes relatively complex group, which is really at the core of all the learning problems. So let me begin, and in that sense, it's a kind of new life because there are a lot of people working on that, but in different community, in all this computer science community of learning. So let me just summarize a bit the ideas of learning. So we are in high dimensions. So we begin with a vector of data notations. Here, x is the function. So when you go from one community to the other, it changes. X is the function, x of t, or x of u. So x is the function or a vector, which belongs in RD, a very large dimensional space. And you want to estimate the label. So for example, for an image, x is an image, typically 1 million pixels. And for an image, you have a certain label. For example, these are anchors, Joshua trees, beavers, lotuses, water lily. So the label is, let's say, water lily associated to these images. So you want to learn this function f of x, that you should really think of it as a functional. Given a set of training samples, so for each image xi, you know the label f of xi. Now you're given a new image, you have to compute the label. So another example of x are audio sounds. So here, the vector is typically about 10,000 samples per second. So again, we are in very high dimension. The other example that I'll be looking at is physics. So still, you have a very high dimensional vector that is going to describe the state of your physical system. And again, you will want to learn a functional. So typically, the kind of functional we'll want to learn here will be the energy associated to the state. So if you think of many body problems, for example, in astronomy, you'd like to learn the energy associated to gravity without knowing anything about physics to begin with. Or we'll look much more in the problems of quantum chemistry. So you don't know Schrödinger equation. You have examples. You are given a molecule. You want to compute the energy of the molecule. In other words, have access to forces and so on, just from a bunch of examples. Can we learn physics? That will be the questions behind that. Okay, so let me come back to why the problem is difficult. As most of you know, it's related to this idea of cursor of dimensionality. You have a bunch of xi, you know the value of the function f of xi, you have a new x. The immediate idea that comes to mind is to say, okay, let's take the xi which are close to x and try to interpolate the value of f at x by some local averaging. For this to work, you need two conditions. F has to be regular, and the second condition is that you need to have some xi which are close to your x. Now, why it's a major failure in high dimension is because you will never have a point xi which is close to x in high dimension. Why? Because if you just take a cube, 0, 1 to the power d in high dimension, if you want to sample your cube at a distance epsilon, obviously the number of points that you will need will be proportional, if I can put that on. No. Is there any pointers? Okay, I'll try with that. The number of points that you will need will be proportional to epsilon to the minus d. So think of epsilon as 1 over 10, which is not very small. D, 100, you get 10 to the power 100, more than the number of atoms in the universe. It's completely tremendous. So it's impossible to make a uniform paving of your domain. What that means is that there will be no xi that will be typically close to x. And that's obvious when you look at images. You take two images of the same class, you compute their Euclidean distance is absolutely non-zero. Worse than that, there is no reason why these two images should be closer than, let's say, these two. So basically, you are in a situation where Euclidean distances are completely non-informative. However, if you have a classification problem, the idea is that somewhere the blue point shares some properties, are closer in some sense than they are to the red points. So there exists some kind of underlying similarity metric that you don't know, but somewhere which exists so that your problem is well defined. So what's the idea of learning? The idea is that what you'd like to do is take your problem, map it in a new space with some nonlinear function phi. Think of phi of x as being a vector of features, so that by miracle, in this space, a simple Euclidean distance will reflect the similarity measure between your points. If you're able to do that, then the blue points are going to aggregate somewhere, and the red points are going to aggregate. So the whole intelligence in the problem is there. The whole intelligence is about understanding what are the distances, what is similar to what, and how to measure this similarity. So it's about finding a mapping which provides some kind of equivalent distance. If you can do that, the problem is simple. The problem is simple. You can easily separate the two classes with a simple hyperplane. In other words, a simple linear operator will separate it, and that's the basic strategy that are used by all these kernel learning algorithms. So where is the difficulty? Setting the hyperplane is not difficult once you've been able to do the mapping. What is really difficult is to do the mapping. How to build this miracle nonlinear mapping so that you'll get an equivalent distance, given that you don't even really know a lot of things about your original distance. Okay, what's the state of the art? What is interesting is that this domain has done a huge step in the last 5, 10 years. What I believe would be unfeasible 10 years ago, let's say within a century, are now almost done. It's really very impressive how this field has improved. In particular, you have these strange neural networks. Neural net, this is an old idea, dates from the 50s, that are suddenly providing very remarkable results. So let's look what are a neural net. A neural net, you begin with your x, and we're going to compute such a phi of x. And how is this phi of x computed? First, by applying a simple linear operator on x, for example, convolution, and then a pointwise nonlinearity to each of the output coefficients, let's say an absolute value, an arctangent, something like that. And then you repeat. You reapply a linear operator, you get an output, and this very simple and the same nonlinearity, you reapply it. And you continue until the point that the output will be your vector phi of x. And now, on this phi of x, you apply a simple linear operator and you classify. So what are your variables in this network? It's all these linear operators. But you can see that if this linear operator takes an entry d and an output even bigger, it's a huge number of variables which are encapsulated within this linear operator. And the whole problem is to learn this linear operator. So what are people doing in practice? In practice, people are imposing constraints on the support of these linear operators, and you'll see it looks very close, in fact, to wavelets. We'll see how they appear. The number of parameters they are going to learn is typically of the order of the billion. How are they learning their parameters? They try to get the best classification results on the training data, and they do some kind of gradient descent on their parameter to optimize the classification result. So, a priori, it should have no reasons to work. In particular, gradient descent is a non-convex problem, blah, 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 and it works incredibly well. Incredibly well, it's not just in academic problems. You have products all over, all the image retrieval of Google, of Facebook, face recognition is based on that, all voice on mail. You have a very, very large number of products which are based on that, which are turning every day in Facebook, Google, Microsoft, Yahoo, IBM, and so on. So the question is why? Why is that working? Why this kind of thing makes sense? And why do we see appearing wavelets, at least in the first layers? So that will be the topic. So the first thing I'd like to show is that at the core of the problem are questions of invariance. How do you build invariance? How do you build invariants which are stable? And we'll see in particular the role of deformation, diffeomorphism. We'll see that this kind of approach provides totally different models, in particular for stochastic processes. Look at complex image classification, and the last part will be devoted to quantum chemistry, and I'll show you how you can apply this kind of thing to learn quantum chemistry. Okay, so let me begin with images. So let's begin with very simple images and try to define a notion of distance. Obviously, these two images, you'll say, are closer than they are to a 5. So why? Well, a natural idea is to say, well, if you measure the deformation from here to here, it's smaller than the deformation from here to here. So a natural metric is a deformation metric. Old idea. How you're going to do that, you define a deformation operator which basically takes your image and warps the space to go, let's say, from here to here. And how are you going to define a notion of distance? You are going to try to warp the space so that the deformation of x is close to x prime, and you are going to measure the distance by looking at the size of the deformation. And the size of the deformation is basically the derivative of tau. If tau is constant, it's a translation, there is no deformation. If the derivative of tau is big, you have a very strong stretching, and that's the classical metric of a deformation, diffeomorphism. In particular, your distance is invariant to translation, and that's natural. An object that you translate remains the same object. Distance should be 0. Okay, why this doesn't work so well? Take a very high dimensional image. Take a texture like that. These two textures, you would say, are typically equivalent and different, let's say, from this one. You would like to define a metric which says that the first two are close and far from the other one. So, okay, so what about the idea of using a deformation metric? If you deform a texture, if the deformation is small, you can still say that the two textures are close. But take these two textures. These are two realizations of Gaussian white noise. They are essentially identical, but you can't deform one into the other. So the deformation metric would say they are very far, although in fact the distance is 0. So you'll want to add the fact that if your two textures are realization of a same random process, which is ergodic, the distance should be 0. So we see suddenly that this idea of deformation is going to be a bit more complicated. And of course, the questions which are behind are trying to understand what kind of models behind these stochastic processes, given that they are not Gaussian, they are not Markov, and so on. Okay, so let's see the information we have. What we want is to define a metric which is going at the end to be Euclidean after your mapping, which is equivalent to your unknown metric. The only thing that we know about the unknown metric is that if you have a small deformation, it should remain small. This is going to be sufficient, we'll see, to very naturally bring wavelets in the problem. So if you have such a property, if you take a deformation which is identity, immediately you see your representation has to be stable to additive noise, or continuous in L2. Phi of x minus phi of x prime should be smaller than x minus x prime. if you take for x prime a deformation of x, what you get is that the representation of x minus the representation of x deformed should be controlled by the size of the deformation. And that will be the difficulty. Obviously, it's very simple to get the first equality. The second one is much more difficult. In particular, it implies invariance to translation, but that's obviously not the difficulty. So let me just show why it's not so easy. Having an invariant to translation or any rigid movement is a very easy thing to do. And translation in particular, you can use the Fourier transform. So if you take a function x, you translate it, you take the modulus of the Fourier transform, Fourier is just going to introduce the phase, the modulus is going to be invariant to translation. In particular, Fourier is continuous in L2. So all this is okay. The problem is deformation. If you take the modulus of a Fourier transform, suppose you just do a very small dilation. In Fourier, the frequencies are going to be dilated. So small frequencies are just going to move a little bit. High frequencies are going to move a lot. And as a result, if you compute a Euclidean distance, it's not going to be small because the high frequency have moved much too much. And that's well known. Fourier is unstable to deformation. This is why nobody's using the Fourier transform for doing pattern recognition. So wavelets. Wavelets, because essentially, Fourier is unstable because when you dilate a sine wave, you have another sine wave of different frequency which is orthogonal. If you dilate a small wavelet, you get another wavelet which is going to be close if the wavelet has been just a little bit dilated. So we're going to use wavelets. I'm going to show it directly in 2D. So the wavelet I'm going to use, think of it as Gabor function, okay, Gaussian modulated by sine wave. My wavelet, as usual, I'm going to dilate it by factor 2 to the j. I'm also going to rotate the wavelet. So these are the wavelets dilated. They are complex. This is the imaginary part, the real part. Rotations, scaling. And here, I'm just going to define a standard little Wood-Paley wavelet. So take the wavelet, in the Fourier domain. That's a bandpass filter, Gaussian modulated. Rotate it, you get all the annulus. Dilation, you get basically the whole Fourier domain. So the wavelet transform here is just a convolution, okay? I have no sampling, no orthogonal basis, okay? And then I'm going also to keep the low frequencies at the end, obviously, to get the very, very small frequencies, which are going to be carried by this averaging over there. If I cover the frequency domain, I'm going to have an energy conservation. This is the Plancherel formula. So I basically have an operator which separates scale, conserves the energy. Okay, so wavelet transform over images. When you separate different scale, you know that. You have the low frequency that you split again into different orientation. Low frequency, different orientation, and so on. So basically, we take the information, we explode it. Now, problem, it's not invariant. How can you build an invariant? If you want to build a linear invariant to translation, you don't have the choice. You need to average. So if you average, let's say with an averaging kernel, imagine a Gaussian dilated, in these signals you'll get that, the black curve. And the black curve, because it's average, is much more invariant to translation. If you want it to be completely invariant to translation, you make a global averaging, so averaging from minus infinity to infinity, you get the average, and obviously it's invariant to translation. But the problem is you lost all the information. And that's the problem with invariant. The real question with invariant is how to build sufficiently rich invariant so that you don't lose the crucial information. Now here, what information you've lost? All the high frequencies. So basically all the wavelet coefficients that you've removed by computing your average. Now the problem is that the wavelet coefficients, here it's a complex wavelets, are oscillatory, so they are not invariant. If I compute the average of that, I'm going to get 0. How can you get an invariant? You can do the same trick than the Fourier transform. You compute the modulus. If you compute the modulus, you're going to get the envelope. The envelope is a little bit more invariant by translation, but it's not. If you translate x, the envelope is going to translate. You want something not covariant, you want something invariant. When your signal translates, nothing should happen. So what are you going to do? What you can do is average. Good. If you average, you are going to get something which is almost translation invariant, or completely, if it's complete averaging. What's the problem? You've lost information. What's the information you've lost? Well, the information you've lost is the complement of this averaging, and the complement of this averaging corresponds to its wavelet coefficients. So you're going to do a new wavelet transform. And you want to make it invariant, you're going again to do a modulus, and you're going to cascade. And what are you going to do? Here's that. You begin with your image, you average. Now you get all the wavelet coefficients and their modulus. They are not invariant by translation. How are you going to make them invariant? You average them. Good. That's the average. That's the complement of information, the next layer of wavelet coefficients. You have to think, you have one image, now you have many images which are exploded into many images and so on. Again, you build invariant from these, that's the average, and now the next layer. And what you recognize, it's a neural network. You are in the sense that you're applying a linear operator, bunch of convolution with wavelet, a nonlinearity, linear operator, nonlinearity, and so on. What is the output? The output are the invariants over there. All the averages. That's what you want to get. Now, the reason why we call that a scattering transform is that if you follow, basically it takes the image and it explodes it following many, many different paths. What is a path? A path is a succession of wavelet convolution with a one wavelet, a second one, a third, and then an averaging. So it's a path across this network. If you want something completely invariant to translation, you let j go into infinity. This is going to give you the integral of this quantity, and therefore this L1 norm. So think of a scattering transform as just being L1 norm, a huge number of L1 norms of cascade of wavelet transform, the one after the other. One thing you can prove is that all the energy of the bottom is going to converge to zero as the depth of the network goes to infinity. Therefore, all the energy of your function is going to be output as invariant coefficients. So here's the transform. You take x, you have first layer of invariance, second, third, just through this cascade. Each operator, so all this cascade was obtained by cascading wavelet transform modulus, and so on. The wavelet transform preserves the norm. But the modulus is contractive. The modulus, you kill the phase, so two numbers are going to get closer after applying a modulus. So the modulus of a wavelet transform is a nonlinear operator, which is contractive. So what that says is that this operator is obtained by a series of contractive operators. So the first property, which is obvious, if you contract, at the end you have something which is contractive. So in the scattering domain, this big vector, if you take an x and a y, are going to get closer than in the original domain. So you have your first property, you are continuous in L2. The second property, like a Fourier transform, you are going to conserve the norm. And the third property, which is what you really want and what we were after, if x is deformed, if you look at the distance with a simple Euclidean distance in the scattering domain, it's going to be bounded by the size of the deformation. And the reason for that is that deformation operators are nearly commuting. The commutator between a deformation operator and a wavelet transform is bounded by the size of the deformation. And to get that, you really need two separate scales. So that's the key reason why you have your stability. Okay, so let's look at applications. Digits. So in a digit problem, you want to recognize a digit given an image of this digit. You have number of digits to learn. What are we going to do? Each digit is transformed with this scattering transform, and then a simple linear classifier. You just separate the space with a hyperplane. If you do that, with that kind of transform, you get the state of the art on this database. It's not quite surprising. This problem is somewhat simple. This problem is all about translation deformation. We linearize the deformation, so we should do well, and we indeed do well. What about textures? So this is a database of textures that comes from Berkeley. You have many, many different materials that have been visualized under different orientations and so on. You want to recognize what material you have. Okay, so a texture is a stationary process. You can view it as an X over there. If you take a stationary process and you make a convolution, it remains stationary. You take a modulus, it remains stationary. You cascade that, all these things are going to remain stationary. If at the end of a stationary process you average, what you can hope is that this is going to converge to an expected value. So, what you are really going to compute by computing this cascade is a bunch of moments of expected value of very nonlinear functions obtained by cascading wavelet transform. And what I want to show is that this set of moments provide very strong characteristic of these processes, in particular of their intermittency property, very non-Gaussian properties. So I'm going to show that. Let's first begin with classification. You just do exactly the same thing then with your digits. You take your texture, you compute the same transform, the same linear classifier. If you do that compared to, in that case, the state of the art, which were not far from Fourier spectrum, you get a reduction which is very important of the error. Why? Because you can discriminate random process having the same second order moment without going to high order moments which have a very large variance. These next layers of coefficients are obtained through contractions. They have a small variance and they characterize, we'll see, these intermittency properties. Okay, if you apply that to this problem, it's not going to work. It's not going to work. You can see here you have textures, but they are very strongly rotated scaled. The error goes to 20%. So you have a very big error. So the problem is the following. Sources of variabilities are not just translation. You have many other sources of variabilities, rotation, scaling, and so on. And the problem is to take care of these. The key idea is that these sources of variability still belongs to group. We're going to do the same thing, but instead of doing wavelets on the translation group, we're going to do the wavelets on rotation group or rototranslation groups. So we're going here to consider the group of all translation rotations, so the special Euclidean groups. So it acts on an image by doing a translation and a rotation. It's a non-commutative group, but we'll see you can still do a wavelet transform. So first, you take your image. The first wavelet transform is going to act on the only variable which is available, translation. You get the average and the wavelet transform. Now, suppose you rotate the image. This is not going to change, but the wavelet transform is going to be translated, rotated, and the index of the orientation of the wavelet is also going to be changed. If you want something which is invariant to translation and rotation, you will need to make your wavelet transform on the translation rotation group, so on these three-dimensional variable groups. And how do you do that? You basically do the same thing. You define your wavelets, and you do a convolution, but the convolution is on the measure of the group. So that's how a wavelet will look like in this group. And when you do the convolution, you do exactly the same kind of integrals. So basically, you do the same kind of thing. You begin with X. You do a wavelet transform on translation to let the rotation parameter and scale parameter appear. And then you do a wavelet transform on the rototranslation group with a convolution with these wavelets, and you cascade that. If you do that on this problem, because you now take care of this variability in rotation, and you can do it for scale, the error drops down to 0.6%. Okay, how much information do you lose? You are building invariants. Are you losing a little bit, a lot of information? So this is a question that we don't understand well mathematically at all, but you can still try to do an inversion. You begin with a transform and try to reconstruct a signal that has the same transform. If you do it with 2 to the j equals to infinity, which we'll do, it's about reconstructing a function from a bunch of L1 norm. Can you reconstruct this function? So I'm first going to begin with stationary processes. For a stationary process, we know that we can't reconstruct exactly the function because we just have a series of expected value. We cannot distinguish true realization, but we can look whether we reconstruct something which is close. So this is a reconstruction from Gaussian model. In other words, what you keep are second-order moments, and you reconstruct from these second-order moments. And that's what you get from this scattering transform. So there's nothing really interesting to look at. If you work with something which has geometry, that's what you have at the top. This is a realization of your random process. This is what you get with a Gaussian having exactly the same second-order moment than that. This is what you get from your scattering coefficient. You can see that because of the interaction of scale and orientation, you capture the geometry, even very long-range geometrical properties. This is yet a different example. This is a very sparse signal, the Gaussian model, what you get. And this is a turbulence example. This is the Gaussian Kolmogorov model of this turbulence example. This is what you recover of this turbulence example. And here the number of moments is just log n squared. So we even keep much less moment that you would keep if you were keeping second-order moments. Let me show you the same thing, audio. I'm going to make you listen the Gaussian model having same second-order moment. The reconstruction from scattering coefficient. Paper. Gaussian. The scattering. Cocktail party. Gaussian. Scattering. You see, you capture the intermittency. Obviously, you don't restore what people are saying, but you capture this intermittency texture property. Can you reconstruct exactly an image? If you begin from very sparse image, like these ones, first-order coefficient, which are just the L1 norm of wavelets, are not sufficient. If you add up the second-order wavelet coefficient, you reconstruct them. Not this one, because not enough sparse, but you get a kind of compressed sensing property. The number of coefficients here are log n squared, whereas the number of coefficients in the image was n squared. So you have a very little number of coefficients, but the image was sparse. No proof why. Okay, let me continue, because I want to arrive to physics. If you do a classifications of very complex problems like that, recognize anchors, nénuphar, bateau, and so on, you do exactly the same thing. And the strange thing is that if you just deal with the geometric invariant, and at the end you do a simple linear classifier, you reach very high relatively high classification results. You have 100 classes. So if you were doing it randomly, you would get 1% of recognition. Here you get 85. With these deep nets, where people learn, they do much better. Much better because here the error is 10%, here the error is 20%. They do much better because they believe that they are learning much more complex groups, and there's all kinds of things to be studied. Okay, let me go to physics. So in physics now, X is going to be the state of the system. And so, for example, in quantum chemistry, X is going to be the position of the atoms and the protonic charge of each of the atoms. So that is specifying the state of the molecule. So how do people usually compute the energy of molecules? So density functional theory is now the tool that is most often used. What you do is you compute the energy as a function of the electronic probability density. So here, for different molecules, you see the electronic probability density, so the density of the electrons around what you see here being the nucleus of the atoms, okay? Now, how do you compute that in density functional theory? So this is the COMSHAM model. The total molecular energy is going to be a function of a number of terms. The kinetic energy, which corresponds to energy due to velocity. You have the electronic and nuclei attraction term, the repulsion between electrons, and then a very complex nonlinear quantum term, which is called the correlation energy. So if you want to compute the energy of the molecule at equilibrium, that I'll call f of x, that's what I want to learn, it's going to be the minimum energy over all possible electronic densities. And in fact, the real electronic density of the molecule will be the electronic density which minimizes the energy. Okay? So, what do you know about this electronic density? You know that if you rotate the molecule, it's not going to change. The energy doesn't change. You know that if you slightly deform the molecule, the energy is just going to slightly change. So you have the same problem, stability to deformorphism, invariance to special Euclidean groups. So we are going to do the same thing. Let me just make a comment. There is one term that is easy to compute, is the Coulomb potential energy. So why do wavelets make sense for a Coulomb potential energy? Well, you have all this work that was done on multipole, and which is well known in physics, is this idea that if you want to compute the interactions, one particle doesn't have to be the interaction, you don't need to compute it with all the other particles. You can just compute the interaction between one particle and the neighbors, and then if you want to compute the interaction with the particle more far away, you can regroup them and compute the interaction as a group. And even more far away, like that. So you have a multiscale behavior in your problem, which you can summarize in a theorem which says that in the case of Coulomb, you can write the Coulomb energy as a linear combination of wavelet coefficients, L2 norm of wavelet coefficients, with very few terms in this sum, just log epsilon term for an error of epsilon. Okay, but quantum is much more difficult. Quantum is much more difficult. You don't have any analytical expression for your energy, and you don't know the density at equilibrium. So how are we going to do? The first thing we're going to do is to make a very crude approximation of the true density by considering that the atoms don't interact. So you have the electronic density of each atom, which you can pre-compute once for all, and you suppose that they don't interact. So you get a very crude approximation of the true density. And we're going to try to compute the true energy from this very crude approximation. So you need to incorporate the error within your regression. How are we going to do that? From a database. Like in image classification, you begin with example of molecules, you have example of energies. We are going to compute for each x the approximate density, very crude approximation, and then we're going to make a regression of this function on all these scattering coefficients. So to do a comparison, I'm going to show the comparison between what you would get with a Fourier invariant to rotation translation, with pure wavelet coefficients, and then with wavelet plus these scattering coefficients. The key idea is that your functional that you want to learn, you are going to expand it within your dictionary, and I'm going to compute a sparse expansion with as few terms as possible. So, this is my, there are several databases. This is a work that was done with a physicist, Nicolas Poelver at Penn State. So from your database, you learn the regression weights with a simple linear ridge regression, and then you compute the average value of the error on a test set. So this is the error as a function of the number of terms you include in the sum. The red curve is what you get with a Fourier dictionary. At one point, oops, you don't see well, okay, it stopped there. Wavelet and Fourier will basically give the same error. Wavelet coefficient will have a faster decay, but at the end, if you put enough coefficient with the Fourier, you'll get the same error. If you include the second order scattering coefficient, this is a log axis vertically, the error drops by here a factor 2 with 400 molecules. It's now you train your system not with 400 molecules, but with 4,000 molecules. The error of wavelet and Fourier doesn't move, and the error of the scattering continues to go down. You reach here 2 kilocalorie per mole. You have to know that when you compute as exactly as you can with density functional theory, the error is only 1 kilocalorie per mole. So with this interpolation, you get an error which is of the same order. So these are the table of value. The state of the art was called Coulomb metric, which is based on multiple distances between atoms. And that's the type of error that you get. Now, the nice thing that you can do afterwards is to compute forces. Because once you have the energy, you can compute the gradient of the energy relatively to your variable. That gives you the forces that you can estimate from these derivatives that you can compute analytically. So we're trying to see whether that kind of thing does give you a good numerical precision. Okay, so the conclusion on all this. The first conclusion is that all these problems, which are really very beautiful, I mean, all these problems of classifications, regressions, and so on, are essentially about Euclidean embeddings. The whole problem is to understand how to take your data, embed it in a Euclidean space so that this simple Euclidean distance in your Euclidean distance space is the right metric that you want. Now, why wavelets? Because as soon as you have a deformation phenomenon, and in all these problems coming from physics, but also all these problems of images, because after all, they come from physics or audio and so on, warping is fundamental. In music, warping is a fundamental element, and it linearizes warping. Wavelets are linearizing metrics over warping. That's why you see over all these neural nets wavelets. Now, what is interesting is that wavelets are not just on translation. I remember at the time, Alex and Thierry were speaking of wavelets over groups. I never could understand why would group come into that, what it would bring. Well, here I finally had to learn groups, and it's fundamental. You absolutely need it because very quickly you go beyond translation. And what is interesting in these problems is that the groups I just described here, translation, special Euclidean group, if you work in music, the natural group will come out from an ellipse, which corresponds to the organization of musical notes. And the groups get more and more and more complicated as you go. And one of the things, as I said, I think, is that these guys with their deep neural net have techniques to basically estimate these groups. So I'm not going to go into that, but these are very nice problems. Now, related to that, there is a phenomenon which is now coming in, which is about learning physics from data. How much can you learn physics from data? So many people were very believing that's not possible, basically. There are more and more elements which shows that, in fact, you can do a lot. And it's not quite surprising because biological systems like electric fish, they learn everything about electric tomography with their little brain, which doesn't include so many neurons. So obviously, there should be ways to learn physics, and it looks like wavelets have something to say into that. And the final thing is, I spoke a lot about groups, but these deep networks, people apply them for natural language, for music. All the natural language system, when you type in English in Google, which is translated in English, it's absolutely not based on syntactic analysis and so on. They take your French phrase, they send it in a Euclidean space, so they build a Euclidean embeddings, which are using these deep networks. Now, you don't have a group structure, you have a grammar structure. Why does it work? What's happening here? No idea, but these are, again, very nice topics. Thanks very much.